Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the failure analysis of the weld joint. In this particular presentation, we will be talking about the cracking of the steel weld joints, the relevant fundamentals, and one case study which is based on the cracking of the high carbon steel weld joints. So, the content of the presentation includes like the cracking in the weld joints, then the detailed aspects of the cold cracking, relevant causes and the factors that affect the cold cracking and how to control the cold cracking. And then one case study based on the failure of the weld joints due to the cold cracking, followed by the failure analysis observation and the findings. So, for cracking to occur in any case, whether it is casting or for the forming or any other process, welding, for cracking to occur, the two things are required. One is whatever the material is experiencing cracking will have the low ductility. Okay. So, if the material is having high ductility, then chances of cracking are decreased significantly. Likewise, cracking will not occur if there is no tensile stresses or shear stress. So, the tensile stresses are more common. So, presence of tensile stress and the low ductility of the material. These are the two, you can say, prerequisite for cracking to occur in the weld joints. And this cracking is promoted in the weld joints by the multiple aspects or multiple phenomenon which will be happening in the welded joints. So, one is the embrittlement, which means a certain metallurgical transformations during the welding will be occurring in the steel, either in the weld metal or in the heat affected zone, in such a way that hardness is enhanced significantly and toughness is compromised, leading to the reduced ductility. Okay. So, the most common embrittlement in carbon steel is due to the formation of the or transformation of the soft phases into the hard and brittle phases, okay, due to the transformation from the soft phases to the hard and brittle phases. So, like say alpha ferrite or perlite transform into the martensite. This can happen in the weld zone, also in heat affected zone. There are multiple other kind of the embrittlements that can happen, like blue embrittlement, temper embrittlement, and likewise there are multiple. But in hardenable carbon steels or alloy steels, means having the high carbon equivalent is high, okay, say greater than 0.4. In all those cases, this tendency of formation of soft phases into the hard phases is extremely high, because during the heating, like say this is the steel component, during the welding, obviously the edges will be brought to the molten state, but the zones which are hit next to the fusion boundary, they will also be experiencing the high temperature, and the molten metal after the solidification will also be forming the austenite, and these phases will also be forming the austenite which are next to the fusion boundary, and away this transformation may be partial, like perlite has transformed into the austenite, or ferrite and perlite both has transformed into the austenite. And this in turn, due to the high cooling rate experienced during the solidification or cooling phase of the weld thermal cycle, these zones are very sensitive for transformation or very prone to form the martensite, okay, in both weld and the heat affected zone. In away, it may be perlite and martensite mixture. Okay. So, because of this, we find extremely high hardness in the weld zone, also in the heat affected in the next to the fusion boundary, and then hardness will keep on decreasing. So, this is a zone where also the hardness is reasonably high. In the weld zone, hardness is extremely high, and because of this, the material experiences the low ductility and brittleness. Okay. And another phenomenon that happens is the development of the residual tensile stresses. Say these are the two components and the weld is being made along the weld center line. So, this weld center line usually experiences very high level of the residual tensile stresses along the weld center line. See, the weld joint experiences very high residual tensile stresses along the weld metal, also in vicinity of the fusion boundary, that tensile residual stresses are experienced, and because of these tensile residual stresses, some tensile stresses are always present in the weld joint, infusion weld joint, and coupled with the low ductility. So, this combination actually makes the high carbon steel weld joints very sensitive for cracking. So, one is the embrittlement, second is the solidification cracks. These cracks primarily happen in the weld joints along the weld center line. Like say, if there are impurities like phosphorus and sulfur in the weld zone, these will tend to get segregated at the weld center line, leading to the excessive presence of the low melting point phases at the weld center line, which under the tensile residual stresses tend to crack. Liquefaction cracks are observed next to the fusion boundary because of the mushy zone formation within the solidus and the liquidus. Okay. So, say this is corresponding to the solidus and this is corresponding to the liquidus. In between we will have a region which will have the two phases, both solid and liquid. So, under the tensile stresses, liquid phase tend to form the cracks because it cannot support the stresses. Underbead cracking will be happening below the weld zone, weld metal, because of the development of tensile stresses, and if there are inclusions which are elongated, then this there is a decohesion between the inclusions and the metal, leads to the formation of the cracks. So, underbead cracks primarily occur when the z direction ductility of the metal is very limited. Like say, the ductility of the metal in direction of the thickness is very less, and if it has the inclusions, so under the residual tensile stresses, the decohesion occurs in these locations wherever the inclusions are present, and that leads to the development of underbead crack. Okay. The one which is very complicated to deal with is the cold crack. Okay. The cold crack, why it is termed so? Because this occurs under the usually at low temperature, like below the 0 degree centigrade, or it can occur also in the ambient temperature conditions. So, since it occurs under the ambient conditions or low temperature conditions, that is why it is called cold crack, not during the welding or just after the welding, but the weld joint has been completely cooled and it has even served for some time. So, then suddenly we will come across the cracks in the weld joints. Since it does not occur immediately after the welding, but it takes some time, maybe 1 hour, 10 hours, 1 day, 10 day, 1 month, 2 months, like that. So, it takes long to develop cracks after the development of joint. That is why it is called, it is also called delayed crack. Okay, delayed cracking. And since this kind of cracking is primarily caused by the presence of the hydrogen coupled with the martensite and the residual tensile stresses or tensile stresses if they are present due to the externally applied loads. So, presence of hydrogen coupled with the high hardness, martensitic phases and the tensile stresses. These three combination of these three factors is needed for the development of cold crack, delayed crack or hydrogen induced cracks. Since this is caused by the presence of the hydrogen, so it is also termed as hydrogen induced crack or hydrogen assisted cracks. So, in this presentation primarily we will try to focus on the hydrogen assisted crack apart from the cracks happening due to the embrittlement. So, we know that when the carbon equivalent is high, increasing carbon equivalent increases the hardenability, which in turn increases the tendency of formation of the soft phases into the hard phases, which makes the weld joint very brittle and crack sensitive. That is why increasing carbon content decreases the ease of welding because of the increased hardenability, increased requirement for preheating to avoid the cracks, or if no preheating is done, then increased cracking tendency. Okay. So, carbon equivalent is the key which is governed by not just carbon, but also the presence of the other alloying elements. About this we have talked earlier, but apart from the alloying elements, the one more factor which also affects the ease of welding and that is the thickness. So, to consider the effect of both, not just the carbon content alloying element, but also consider the effect of thickness on hardening and cracking tendency, a compensated carbon equivalent is also calculated, which is composed of not just carbon equivalent based on the carbon and alloying element proportions, but it also considers the thickness. Okay. So, this thickness T is in mm. So, a few empirical things have been developed considering the carbon equivalent and whether we should use preheat or we should not preheat. Means based on the carbon equivalent or compensated carbon equivalent, ease of the welding or the weldability is identified. So, if the compensated carbon equivalent is less than 0.4, then no preheat is required and the welding can be done reasonably good without much difficulty. But if the carbonic CCE is in the range of zero point 0.4 to zero point 0.7, then with the degree of preheat of 200 to 500 degrees centigrade, the welding can be done, and it becomes extremely difficult if the compensated carbon equivalent is greater than 0.7. Okay. So, the thing here is when the CCE or when the CE is extremely high, it increases the tendency of the formation of the extremely high hardness and induce the brittleness coupled with the low ductility, and these in turn increase the cracking tendency, especially in presence of the tensile stresses. Okay. So, this is what is showing that in a typical weld joint, okay, let us say this is the weld joint, all right, this is the weld center line, and here a weld has been developed. Okay. So, in the weld zone we will see that at the center that stresses are maximum and these are tensile in nature. In vicinity of the weld, the stresses are compressive in nature to balance the things, but this is one aspect. Along the weld metal, the stresses are tensile in nature, and also close to the fusion boundary, stresses are tensile in nature. But when we use the high strength filler metal, the higher residual stresses are induced, and when we use the low strength filler metal, the maximum residual stress magnitude that is induced is lower. Okay. So, this is one of the aspect, like for developing the weld joint, if we use the low strength filler, then the magnitude of residual stress that will be induced will be lesser. And one more thing, that the maximum magnitude of the residual stress that can be induced is equal to the yield strength, because if it is greater than that, then the wrapping or distortion will happen, or the material will tend to behave very erratically. Okay. So, this is showing that effect of the filler metal choice on the residual stress development. This is one aspect. Second is along the weld line or along in the weld metal, residual stresses are tensile in nature. Okay. So, when the hardenability is high, obviously material will show the greater tendency for increased hardness and low toughness, low ductility. Okay, high hardness and the low ductility. And when it is combined with the residual tensile stresses, it shows the cracking tendency. So, here in this case no need of the hydrogen actually, because material itself is showing extremely high hardness, low ductility. So, under the tensile stresses it will be showing the cracking. So, here to avoid this kind of the cracking, what should be done is somehow efforts are made to reduce the residual tensile stress. For that we may use preheating or low strength filler, or use the groove geometry in such a way that the volume of the weld metal being deposited is very limited. The another way is do the proper preheating, so that the high cooling rates are avoided, to avoid the formation of hard and brittle phases like martensite, and the soft phases are encouraged, so that embrittlement of the weld metal and the nearby heat affected zone is minimized. That is what we can see here. If the two sides we have the different kind of the metals, with both are showing the transformation hardening behavior, then the next to the weld zone, means heat affected zone, there will be increased hardness tendency. The weld metal composition can be designed using the suitable filler. If it is the matching, then hardness will be more, and if the filler is of the low yield strength, then hardness will be low. So, the good part in fusion welding is that using filler, the hardness of the weld zone can be adjusted, can be regulated to avoid cracking tendency, but not much can be done as far as the heat affected zone is concerned. So, that has to be technologically managed by using proper preheat in order to avoid the embrittlement and excessive hardening and cracking tendency. As far as cold cracking is concerned, cold or delayed cracking or hydrogen induced cracking is concerned, these are the four things which are needed. One is primarily it is three, like the hydrogen content must be greater. So, like 4 or 5 ppm of the hydrogen also can cause the cracking, high tensile stresses and susceptible microstructure like martensite. If these three are present, it will show the greater tendency, especially also when the weld joint is exposed to the lower temperature condition, maybe ambient temperature or below the room temperature, then also the cracking tendency is increased suddenly. So, these are three main factors that contribute towards the hydrogen induced cracking. And what happens during the cracking? Let's say this is the weld joint. Weld joint, say weld metal is of the low strength using say nickel or austenitic stainless steel, and this base metal is of the high carbon equivalent. So, it will showing the greater cracking tendency. So, what happens when the weld joint is made? So, the hydrogen is diffused in the heat affected zone. Okay. So, diffused hydrogen starts getting segregated at certain vacancy locations here and there, builds up the pressure. When the pressure in the vacancy zones exceeds the material's fracture strength, crack starts propagating. So, once the crack propagates, pressure is released. So, the hydrogen diffusion towards the vacancies, crack growth rate and then relaxation of pressure, this cycle keeps on repeating, and eventually we will see that so this takes some time first to crack nucleate, okay, then crack will be propagating and then finally fracture will be happening. Okay. So, if the hydrogen is less, crack propagation will be, crack incubation time will be long, and it will take long for initiating the crack, then crack growth rate and finally fracture. So, everything gets delayed. When the hydrogen is high, then everything will be finished earlier, and in that case, like say the crack will the hydrogen will diffuse towards the vacancies, then crack will initiate, then it will be growing and then finally fracture will be taking. If the hydrogen is less, then these tendencies are minimized significantly. So, how, what we can say here, when the applied stress or residual tensile stress, whatever it is, so the time relationship as far as the hydrogen induced cracking is concerned, for a given level of a hydrogen for a given microstructure which is also sensitive for cracking. So, what happens when the stress level is low? It takes long to initiate, then propagate and then finish the and to cause the fracture. When the stress level is high, it takes very less time to initiate the fracture, then complete the propagation and then cause the complete fracture. So, the applied stress and the time relationship for hydrogen induced cracking is shown in this diagram. What this diagram shows is the effect of hydrogen and the material strength. Okay. When the hydrogen content is low, it takes very long to nucleate and then propagate and then cause the final fracture. But when the hydrogen content is extremely high, for a given stress level, at high hydrogen level, the cracks nucleate early, easily, quickly, and then the fracture is caused quickly. So, it is very important that hydrogen content in the weld zone, either in the weld metal or in the heat affected zone, is minimized. Okay, this is the key. So, use the low hydrogen electrode, that is one. Use proper preheat so that soft phases are formed or hydrogen gets enough time for escaping, or use such kind of the electrodes which are soft, ductile and they absorb impurities, develop lower residual stresses because of low strength. So, these will be helping to avoid the hydrogen induced cracking. On the other hand, when we work with the high strength steels, so we can see with for a given applied stress with the high strength steels, the cracks are nucleated and propagation is completed, fracture occurs quickly as compared to the case of the low strength metals for a lower level of stress. That is what we can see. For moderate level of stresses, in the case of high strength steels, the fracture occurs much earlier as compared to the case of the low strength steels, and moderate one for the medium strength steels. So, this is what we can see here as far as the applied stress and the time relationship is concerned. So, what can be done to avoid the hydrogen induced cracking or hydrogen assisted cracking? One, use the low hydrogen electrodes. Okay. So, like the basic electrodes are chosen instead of the cellulosic. So, they generate lesser the hydrogen. use proper baking of the electrodes, so that if there is a moisture, that is driven off, because moisture eventually be converting into the vapors which will decompose and produce the hydrogen. Use the welding processes which do not involve the flux, so use the gas tungsten arc welding or gas metal arc welding processes, and use suitable preheat. The advantage is that our cooling rates are reduced with the preheat. High temperature retention time is increased, so that will be giving enough time for the escaping of the hydrogen during the solidification and during the cooling. The another thing is like avoid the hard and brittle phases. So, this the first zone deals with the reducing the hydrogen level. Second step or second approach deals with the developing soft phases. So, avoid the hard and brittle phases like martensite, and that can be done by using proper preheat. So, that preheating will reduce the cooling rates and will encourage the formation of the soft phases like perlite, ferrite, benite, etc. And vary the welding parameters in such a way that try to increase the heat input using the suitable combination of the VIS in case of the arc welding processes, so that the soft phase formation is enhanced. Okay, or the multi pass welding can be achieved, so that the bead tempering will be done, and that will be reducing the tempering will help to reduce the toughness or reduce the hardness and increase the toughness of the earlier deposited beads. And as a thumb rule, no preheat is needed if the carbon equivalent is less than 0.4 and for thickness less than 35 mm, and it will not be susceptible, steel will not be susceptible for the hydrogen assisted cracking if the hardness is less than 350 VHN. Okay. So, what can be done, as I have said, when preheat is used, it reduces the hardness due to the formation of the soft phases. It increases the time for escaping of the hydrogen. So, diffused hydrogen content in the weld and the heat affected zone is minimized, and it promotes the formation of the soft phases like ferrite, perlite and benite as compared to that of the martensite without preheat. So, the preheating is very crucial in that way, because it is not just promoting the soft phase formation, but also helping in to reduce the hardness and reducing the hydrogen level. So, all these three things will be favorable with regard to the control of the hydrogen induced cracking. So, the preheat is very crucial. So, there are two ways to determine the preheat. One is preheat temperature. One is the composition based, where we try to determine the carbon equivalent, and based on the carbon equivalent we try to identify suitable preheat and interface temperature for the welding. And the second is the hardenability based approach to avoid the cracking, which considers like the residual stress and the hydrogen content and the other aspects, material aspects. Okay, so this preheat temperature determination is based on the one Gravely diagram, which considers the carbon equivalent, and based on that the weldability aspect is determined. So, the carbon equivalent and the carbon content, these are the two aspects. So, when the carbon content is about say 1.13 and for entire carbon content is about 1.3, and the carbon equivalent is over a wide range. So, this forms a zone which is easily weldable. Then there is a zone 2 where the carbon content is greater than say 1.3, but the carbon equivalent is in this band, that is the weld zone 2, weldable zone, but with the preheat, and this is non weldable zone, this is zone 3, and here the carbon content is high and carbon equivalent is also high. Okay, so this is how we can determine the carbon equivalent, and here preheat temperature based on the carbon equivalent. This is a hardness control approach. Here what we do basically, the carbon equivalent is in the x axis and the y axis. Suitable preheat temperature is used, which can range say from say 20 degrees centigrade to 40 degrees centigrade, and the carbon equivalent say 0.2 to say 1.2, and we get a band like this depending upon the thickness and the material compositions. So, here we have a band which is helpful to determine, you can say this gives you a range of the temperature for the different carbon, for different preheat temperatures for different carbon equivalent. So, this is the hardness control approach, where suitable preheat will reduce the cooling rate, and that in turn will encourage the formation of the soft phases, good for the zone 2 of the Gravely diagram. There is a hydrogen control approach which is applicable for zone 1 and zone 3 of a gravity diagram. What it considers like the composition aspect, that is based on the carbon content, silicon, manganese, copper, chromium, nickel, vanadium and the boron. So, this is considers the composition, then the diffused hydrogen and the restraint that will be determining the residual stresses. So, these factors are determined and so what we do, so here Hd is the diffused hydrogen and the K is the like the Weld strain, that is based on the K naught H. K naught is constant and K H is the thickness. So, based on this these three parameters are used to determine the value of the Pw, and then Pw is used to calculate the temperature that should be used for the purpose of preheat. Okay. So, one of the simple approaches of the controlling hydrogen induced cracking is use of the multi-pass welding. So, like say this is the weld joint. So, edges have been prepared. So, what we do? The welding is done in number of passes like this. So, obviously, the subsequent passes will be depositing some metal over the earlier deposited passes. So, this will be applying, not just causing the remelting, but also applying a little heat for the tempering purpose. So, this process like multi-pass welding actually helps in tempering the earlier deposited beads. So, this the tempering helps to soften and relieve the residual stresses, refine the grain structure. So, multiple benefits are achieved through this bead tempering approach. And if the application allows use of the low strength filler, then that will help in reducing the residual stresses as I have described earlier. So, instead of using the high strength weld filler metal for developing the weld joint, so if you use high strength filler metal, then the residual stress distribution will be like this, and if you use the low strength filler, then residual stress distribution is minimized like this. So, the maximum stresses that are being developed, that will be reduced, and that in turn can decrease the tendency of the cracking. Okay. Another way of controlling the HIC is use the low hydrogen processes and consumables, which includes like use of the GTA or GMAW processes instead of the flux core or instead of flux based processes like shielded metal arc welding and the flux core arc welding. Use the low hydrogen consumables like basic electrodes rather than the cellulosic electrodes, and do the proper baking so that if there is any moisture, that is driven off in order to avoid the presence of hydrogen in weld metal, which subsequently will be diffusing into the HZ and making it sensitive for cold cracking. The post-weld heat treatment helps in number of ways, like once the weld joint has been developed, that's very hard, very brittle, having a lot of residual stresses and martensitic phases in the weld and the heat affected zone. So, if we do the post weld heat treatment in the range of like say 590 to 675, then what it will be doing? It will be relieving the residual stress. So, the residual stress magnitude will be reduced. Okay. Then it will induce the soft phases, martensite will be tempered. Okay. And exposure at high temperature will help to diffuse out the hydrogen from the heat affected zone and also the weld metal. So, these three things are achieved, and all these three will be helping in to reduce the hydrogen induced cracking tendency. So, let us talk about one the case study of the failure analysis of the weld joint of a machine component. Say a structural member of the machine component made of the high carbon steel. So, this is the means the carbon equivalent say is greater than 0.5, which makes it very sensitive for martensitic transformation and increased embrittlement of the weld zone. Okay. This component failed prematurely within the 4 months of service and investigation undertaken, and it was found that the material is made of 1050 AISI 1050 is steel composition as specified. So, this part is fine. Okay. Design as per the recommendation. So, there is no issue as far as the design aspects is concerned. Visual examination of the failed component or failed weld joint indicated the brittle fracture without any sign of the deformation. Okay. So, this indicates the embrittlement tendency. Welding was done using the SMAW electrodes, shielded metal arc welding without preheat and post weld heat. So, this indicates a lot, like SMAW having the greater affinity or greater possibility for providing the hydrogen, and the no preheat and the no PWHT means there is increased tendency of the embrittlement, not just of the heat affected zone, but also of the weld zone. Mechanical properties in terms of hardness shows very high hardness of 540 HV as compared to that of the specified 250 HV. Microstructure indicated the untempered martensite in the weld as well as heat affected zone. And considering the fracture behavior, also the gas analysis was carried out, and it was found that diffused hydrogen in the weld was 20 ppm. Residual stress study indicated 200 MPa of the tensile type residual stress in the weld metal. Operation was normal, no maintenance requirement, and stereoscopy and the SAM indicated the intergranular fracture that is typically indicative of the hydrogen-induced cracking and with few cleavage facets without any sign of determination. Comparison of this field sample with the new one indicated higher hardness, higher hydrogen, higher residual tensile stresses, and tempered martensite. Okay, so all above suggested that component failed by the cold cracking because of the improper preheat, means there was no preheat, and PWHD, there was no PWHD, and also high hydrogen content, and not appropriate filler was used because the weld metal was also showing extremely high hardness. So the use of the low fillers, proper preheat, and proper PWHD could have avoided this kind of cracking. So now I will summarize this presentation. In this presentation, I have talked about the different types of the cracking observed in the steel weld joints, and we have talked about the factors that contribute towards the cold cracking and what can be done to avoid the cold cracking. And also I have taken one case study on the failure analysis of the weld joint of the high carbon steel component. Thank you for your attention.